The paper we're taking a deep dive into today is titled Reward Modeling from Natural Language Human Feedback, and it comes from the Tanguy lab at Alibaba Group. And if you've been wrestling with how to get genuinely useful critiques out of your large language models, well, this paper hits right on the core pain point, so let's just get straight to the key insights. The problem they're tackling is with Generative Reward Models, or GRMs. Right now, these are mainly trained using a simple binary outcome. Did the model choose the right answer, yes or no? But the authors found this huge flaw, something they call outcome process inconsistency. Basically, in these simple binary choice tasks, a GRM can just guess the right answer, and it does so 20 to 30% of the time, even when its reasoning is completely wrong. And that introduces this massive destabilizing noise into the reward signal. It's really poisoning the well. Their solution is called RM-NLHF, which stands for Reward Modeling from Natural Language Human Feedback. Instead of just relying on that simple yes-no outcome, they introduce a process reward. This is a signal based on how similar the model's critique is to a gold standard human critique. So it forces the model to learn sound reasoning, not just how to guess correctly. Now, human critiques are really expensive to get. So to make this scale, they built something called the Online Meta-Reward Model, or MetaRM. It's a smaller model that learns to predict the process reward from just a small set of human data. And then it generalizes that knowledge across huge unlabeled data sets, and crucially, it adapts as the main model gets better. The bottom line is that RM-NLHF consistently beats the best GRMs that are trained with only outcome rewards. It produces critiques that are more accurate, more diagnostic, and actually useful for downstream tasks. It's about moving past the guessing game.
It really is. And what's so fascinating here is that they've managed to quantify a problem that, a lot of researchers have seen anecdotally for years. We're talking about these generative reward models, GRMs, which were supposed to be a big step up from the old scalar reward models.
Right, because they generate that detailed rationale, the natural language justification, before they even make a judgment. They're supposed to show their work.
Exactly. They were supposed to be more robust, more generalizable for complex tasks. But the flaw isn't in the GRM idea itself, it's in how we've been training them, this thing called reinforcement learning with verifiable reward, or RLVR. It just uses that simple binary label.
Okay, so help me understand the solution space issue here.
Well, think about it like this. If you're doing a complex math proof, the number of possible paths is enormous. So if you get the right final answer, it's very, very likely your reasoning was also correct. But with a pairwise preference task, you have two choices, A or B. The solution space is tiny.
So the model has a 50-50 shot of just guessing the right letter, even if the critique it wrote to justify that choice is complete nonsense.
Precisely. That tiny solution space makes it incredibly easy for the model to latch onto some superficial feature to guess the right answer, even when its critique is fundamentally flawed.
And the authors, they really put numbers to this. They didn't just speculate.
No, they did a comprehensive analysis, and they found that this outcome process inconsistency is a huge problem. We're talking 20 to 30% of correct outcome predictions were backed by critiques a human would say are just plain wrong.
That's an incredible amount of noise.
Yeah.
So you're giving the model a perfect score, a one tight, but up to a third of the time, the reason it got that score was bogus.
It's pervasive. And they even saw this in really sophisticated proprietary models, not just open source ones. The examples they give are just perfect at illustrating this.
Tell me about the French Revolution one.
Right. So the GRM correctly chose response A, the one that was historically accurate, but its critique said that both responses were factually correct.
Which they weren't.
No, the human critique clearly pointed out that response B had major historical inaccuracies.
So the GRM basically hit the bullseye while wearing a blindfold. It got the right answer, but its own reasoning was objectively false.
Exactly. And then there's a second, even more subtle example about writing a comforting message. Here, the GRM chose the wrong response, B, and its critique focused on B having upbeat energy. But the human critique flagged that same response for toxic positivity. The model completely missed the core emotional flaw.
It was focused on a surface-level detail instead of the actual point of the task. That's the problem with outcome-only reward, right? It doesn't penalize the model for missing the point.
Exactly. It only penalizes it for picking the wrong letter. The model gets rewarded for writing something that sounds like a critique, even if it's a terrible one.
Okay, so they've clearly identified the problem. The next logical step must have been, how do we build a better reward signal? A proxy for that deep human reasoning.
That's it. They started with a small, curated data set, just 49 samples, but they had everything. The query, the responses, the model's critique, and the gold standard human critique. And they tested a few different ways to measure the goodness of the model's critique.
What was the first thing they tried? I'm guessing they just threw another LLM at it.
You guessed it. They tried an LLM as a meta-judge approach, just asking a powerful external LLM, is this critique any good?
And
It failed spectacularly, just completely unreliable. It had the worst performance with gaps up to 59%. So that idea was out.
wow, a 59% gap. So just asking a model to grade another model's reasoning is not as simple as it sounds.
Not at all. The much more successful approaches all centered on similarity metrics. They tried measuring the similarity between the model's critique and the human critique.
But they made a key distinction, right, between all the critique points and just the core points.
Yes, and that proved to be crucial. When they measured similarity with only the core human critique arguments, performance was much better. They realized that all the minor nitpicky points were just adding noise.
So you have to focus on the essential arguments to get a clean signal.
Exactly. They settled on using the F1 metric for the similarity, and they found they could use a pretty cost-effective model, something like GPT-5 Mini, to do the calculation.
That's a great practical detail. You don't need some massive, expensive model just to calculate the similarity.
Right. And this gave them their process reward, the process. They then combined it with the outcome. The final reward is 1 plus some weight times the process reward, but, and this is critical, only if the model chose the correct preference.
So that's the outcome regularization.
Right.
What happens if the GRM gets the preference wrong?
It gets a 0 instantly. The process reward is completely ignored.
Why is that so strict? Is there a risk you might miss a really good critique that just happened to make the wrong final choice?
It's a fair question, but their data showed that an incorrect outcome almost always meant the critique was also bad. This rule is what stabilizes the whole RL training process.
So without it, the model could drift. You could learn that it's okay to be wrong as long as its reasoning sounds plausible.
You'd get catastrophic drift. You'd be rewarding flawed logic. This way, the model has to get the main objective right first, and only then does it get points for the quality of its reasoning.
And the early results showed this worked.
Immediately. They saw significant and consistent improvements in both accuracy and the average process reward score. The process supervision was clearly doing its job.
But this brings us to the elephant in the room. Scale. Getting high-quality human critiques for millions of examples is just not feasible.
It's the key challenge. Most of our existing data sets just have those simple binary outcome labels. You can't just throw them away.
So this is where the meta-reward model, the MetaRM, comes into play.
Right. The MetaRM is a smaller, separate model. You train it on your small, high-quality data set that has all the human critiques. It essentially learns to predict what the composite reward score would be. You're basically distilling the human expert's judgment into this little model.
So you train this MetaRM to be your expert grader, and then you can send it off to grade the millions of unlabeled examples.
That's the idea. But they had a big technical hurdle that anyone in RL knows well, distribution shift.
Explain that. Why does a model trained at the start of the process become useless later on?
Well, the main GRM is constantly learning and improving. So the critiques it generates today are very different from the ones it generated last week.
Okay.
If you train your MetaRM just once at the beginning, an offline MetaRM, it's only calibrated to judge the outputs of the initial pretty bad GRM. As the GRM gets better, the MetaRM becomes miscalibrated.
It's like a teacher using a grading rubric from 5 years ago doesn't know what good work looks like anymore.
That's a perfect analogy. That's exactly it, which is why they had to develop the online MetaRM framework.
So it's constantly updating.
In continuous loops. In each step, they feed it fresh examples from their small human-labeled set to recalibrate it to the current GRM's outputs.
So it's always learning what the new good looks like.
Yes. And only after that calibration step do they use the updated MetaRM to predict the rewards for the huge unlabeled dataset. This continuous adaptation is what prevents the miscalibration.
And the results must have shown how necessary this online approach was.
Oh, absolutely. The online MetaRM consistently and substantially outperformed a frozen offline one. And here's the punchline. It achieved performance that was almost as good as the hypothetical best-case scenario, where they had human critiques for every single sample.
But with a tiny fraction of the annotation cost.
A tiny fraction.
Yeah.
They also noted that trying to mix and match using process reward on the small data set and just outcome reward on the big one was catastrophic. It just sent conflicting signals to the model.
Right, you can't have two teachers with totally different grading systems. You need consistency. Okay, let's get to the main results. This is where all that clever engineering pays off. How much better did this RM-NLHF perform?
The jump was really substantial. It achieved state-of-the-art performance against other specially trained GRMs of the same size. To give you some numbers, the RM-NLHF Q17B model got an overall score of about 0.65.
And the baseline?
The baseline, trained with outcome-only reward, was down at 0.57. That's a huge leap in accuracy just from fixing the reward signal.
It really is. What about scalability?
This was another fascinating insight. The GRMs trained with their methods scaled much more effectively with model size. They saw big improvements going from 7 billion to 32 billion parameters. But the old scalar reward models, they barely improved, even when they were scaled up to 70 billion parameters.
So it suggests that if your model can't articulate why it's making a choice, just making it bigger doesn't really help it get smarter.
Precisely. The ability to generate a critique seems to be what allows these models to actually leverage the extra parameters.
And does this improved critique quality actually help in real-world applications?
Yes, and that's the ultimate test. They checked it on 2 downstream tasks. First was best of n, which is just picking the best response out of a generated batch.
And it was better at that.
It was, especially on a tough benchmark like human evil plus calms. But the really big gains came from the second task, which was feedback edit.
This is where you use the model's critique to actually fix a bad response.
Yeah.
Right? It tests how actionable the feedback is.
Exactly. If the critique is just superficial fluff, an edit model can't do anything with it. But the critiques from RM-NLHF led to substantial improvements in the refined responses.
So it's direct validation. The critiques aren't just sounding better, they're genuinely more useful.
They're diagnostically useful, yes. And importantly, the computational cost was pretty manageable. With some asynchronous execution, the overhead was only about a 26% increase for the 7B model.
Given the performance gain, that seems like a trade-off you'd make every time.
Absolutely. But maybe the most illustrative part of the whole paper is the linguistic analysis they did. They looked at the actual words the models were using in their critiques.
How did the vocabulary change?
The difference is night and day. The RM-NLHF model used over 4,400 unique words in its critiques. The baseline, only about 1,600.
Wow. That's a massive shift away from just using templated, generic feedback.
It is. And when you look at the specific words, the story becomes even clearer. The RM-NLHF model started using sharp diagnostic terms like unusable, critical, incorrect, unrelated.
Words that point to a real, specific flaw.
Right. And the baseline model, the one trained only on the outcome, it over-relied on these generic positive-sounding words like provides, comprehensive, and clear.
It learned to generate feedback that just sounded good enough to justify its choice, but it wasn't actually finding the core issues.
That's the takeaway. By adding that explicit process reward, they forced the model to become a much better, much more detailed critic. It had to learn to find the real distinguishing factors, not just fill space with platitudes.
So to sum it all up, they identified this critical flaw, the outcome process inconsistency, and build a really scalable system with the online MetaRM to fix it.
They really did. Of course, there are always limitations. The whole system depends on having high-quality human critiques to start with for that small seed dataset. If your source critiques are bad, the MetaRM will learn bad judgment.
And it might struggle in really open-ended domains where there's no single right answer.
Right, or where cultural preferences are really diverse. But the core idea, this method of getting a process-level reward, is hugely transferable.
Where else could you see this being applied?
Well, think about any task with the small solution space. Multiple choice questions, true-false questions, all of those areas could benefit. Or even complex tasks like code generation or mathematical proofs, where verifying the process is just as important as the final answer.
So here's the final thought to leave you with. We've just seen how RM-NLHF helps a reward model generate critiques that are way better for tasks like feedback edit. How long until we see this method move beyond just training reward models? When do we start using it to directly train the large generative models themselves, to give them the ability to offer their own explicit high-quality feedback during their own internal self-correction loops? That ability for a model to reliably and deeply critique its own reasoning, that feels like the next major frontier.